Okay, so like we said yesterday, we just need to complete this last verification for our rods. Basically, what we call combined axial force and shear. So yesterday we found out that the rods are well designed in terms of axial force verification, but we said also, buongiorno, that this connection, in addition to the bending moment, the axial force, we also have a shear. So this beam here is subjected to a shear along this shearing plane here. So all the rods will have to resist also some shear that will have to be combined together with the axial force using this quadratic criterion. As we said yesterday, the quadratic criterion is not very severe. It's much less severe, if you want, compared to the linear interaction criterion. However, we need to ensure that this ratio, which is basically the ratio between the demand and the strength, so we need to find out the demand of axial force in the most stressed rod, and to do the ratio with the resistance of the most stressed rod, to do the ratio to the power of 2, and then to sum the other ratio between the demand of shear and the shear resistance, always for the most stressed rod. So as we said yesterday, the most stressed rod, if you remember, is the first on the right hand side. So this one is the one which is subjected to the highest compressive load, to the highest compressive load. And so we will have to check, basically, that the combination between this axial force and the shear force will satisfy this interaction criterion. So we start by calculating the demand, so the demand in terms of compression force. This comes from basically this solution of the third-degree equation that we did yesterday, and then with the use of basically the Navier equation to find out the axial force here. So we found out yesterday, if you look back to what we did yesterday evening, we found out that it was the maximum stress demand was 242.3 megapascal. So we multiply this by the resistance area of one rod, and we find 59 kilonewtons. So this is the demand. The strength was 62 kilonewtons. This was the strength that we found out using the buckling formula, if you remember. So first we checked the rods for basically yielding, but then we realized that in compression we have also buckling. So we checked the buckling resistance with this kind of Euro 3 formula. Same thing that we did for the screws in the past. And we found out that we had like, I think 10 or 15% less resistance compared to yielding due to the problem that this compressed rod can make buckle. So this was the resistance. As you can see, we have a quite high utilization ratio in the sense that the demand is 59 kilonewton and the strength is 62, so we're very close to each other. So there is a concern that actually when we sum up to this, we combine with shear, we can actually get a ratio which is higher than 1. So we have to check it. Because we are very close to the, let's say, the actual resistance. So, calculation of the shear demand. In terms of shear demand, we have basically a situation like this. So this is the beam, this is the column. If we have a shear, for example, like this, or we have actually in this case, I think the shear like this, probably, remember well. So we will have that this rod will deform in this way. So the rods will, in this respect, the rods will behave like bolts or like dowels. So in shear, we need to consider the Euro 5 equation, so the Johansen equation that we derived in the past and that we use also for screws, nails, and bolts. So we have an overall number of 12 rods. So the demand in terms of shear will be the actual shear force divided by the number of rods. So 1,892 kilonewtons, so 1.8 kilonewtons basically. And then we need to calculate the shear capacity. So the shear capacity is calculated using the Johansen formula for the bolts. So we're going to see what we found for our Johansen equations for the bolts. And just we need to replace the diameter of the bolts using 90% of the nominal rod diameter. So our nominal rod diameter is 20 millimeter, so 90% of 20 millimeter is 80 millimeter. So we are going to use the Johansen equation using a diameter of 18 millimeter. This is just to allow for the fact that the rod is not smooth like bolts, but we have a threaded rods, so there is a difference between the nominal diameter and actually, for example, the diameter of the thread and the diameter of the inner part of the thread. So there is basically this is what we have something like this. So the nominal diameter is usually the outer one, so this is the nominal diameter. We need to consider kind of 90% of the nominal diameter in our resistance when using the Johansen equation. So the lateral, so we calculated the shear demand for a single rod. And then we need to calculate the shear resistance of a single rod. So the shear resistance of the single rod will be calculated by taking also into account the fact that some of the rods are aligned parallel to the grain. So on the beam side, we have that the rods are aligned parallel to the grain. So we need to take into account that we have an effective number, LEF, which will be lower than the actual number. And then the usual formula, the multiplication factor times characteristic shear strength, calculated using Johansen, and divided by gamma and safety coefficient. So we have two groups of rods. The tensile rods are 2 aligned, and the compressive one are 4 aligned. So the worst case scenario is the one with 4 aligned. So NEF for 4 aligned rods will be given by this equation. So N will be 4 to the power of 0.9 times A1 is the spacing between the rods, so 100 millimeter, divided by 13 times the diameter, 8. This is to the power of 1. So in the end, the 4 rods are equivalent in terms of shear resistance to 2.82 rods, effective rods. And then we calculate FVRK using the Johansen formula for both the timber-to-timber connection. In this case, we have to consider that the regulation said, the CNR regulation said that for rods glued in perpendicular to the grain, so for the rods that are glued in perpendicular to the grain, so on the side of the beam, characteristic and bending strength calculated with the formula for the bolts can be increased by 25%. While instead for rods glued in parallel to the grain, so on the column side, characteristic and bending strength is assumed 10% of the bending strength perpendicular to the grain. So first we calculate this one. Actually, first we calculate the bending strength of a bolt. Then we increase by 25% to get the bending strength of the glued in rods in the beam. And then we reduce by 90% to find out the bending strength of the glued in rods in the column. Okay, so this is what we have to do. So this is a kind of connection between timber-to-timber connection, as you can see. So we have this set of 6 equations from the Euro 5. In order to find out the characteristic shear strength of a single glued in rods, we need to consider 6 different failing mechanisms, as you can remember. We start with pure embedding. So we need to define FH1K, so the bending strength on the beam, the bending strength on the column, the thickness, well, T1 and T2 actually are the length, as we will see, of the rods in the beam, the length of the rods in the column, is diameter. Beta is the ratio between FH2K and FH1K, so the ratio between the two bending strength. Then we need to calculate the axial capacity, so what is called in English withdrawal capacity of the rods, so the axial tensile capacity of the rods in some way. We need to calculate the yielding bending moment of the rod, so MYRK, and then we are ready to input all this value in this fixed format to find out the actual shear strength capacity. So, T1, so we assume that 1 is the member, so we call with 1 the column and with 2 the beam basically. So T1 will be 1000 mm because T1 is the length of the rod on the column side, and T2 will be 500 mm, so the length of the rod on the beam side. We said before that the bending strength FH1K in the column will be different from the one for the beam. So the one in the column will be only 10% of the one in the beam. And the one in the beam will be 25% more of the bolt one. So we need to take into account that the rod is excluded somewhere. We need also to take into account this thing here. As you can see here, well, as you may recall, in the Johansen equation there is also the rope effect. The rope effect takes into account the fact that some way there is an increased strength due to the fact that there will be additional friction. Now, in terms of a glued-in rod, there is no indication in the regulation. As I said before, in the Euro 5 there is no indication at all about glued-in rods. There will be some more, there will be a new clause or a new paragraph in the new version of the Euro 5 which will be released later on. So for the time being, we need to choose between round nails, square and groove nails, other nails, screws, bolts, and dowels. Now, in terms of withdrawal strength, so axial capacity, what do you think? It says, which one of those is closer to a glued-in rod? So since the rod is glued, we can expect that it will have a quite significant withdrawal capacity. So for this reason, I would say that the closest one is the one for screws. Because the screws is, if you can see, the screw is the best one. Because the screws has, because of the thread, it has a continuous bond with the wood. In our case, we have a threaded rod, like a screws, which in addition is also glued. So like a screw glued on the tipper, so it's even better. So I would say we take the highest value, the one from the screws, okay? Because we have no indication. So this means that the rope effect may be up to 100% of the first term of the Johansen equation, okay? So now we need to calculate, first of all, the characteristic value for the yield moment of the glued-in rod using this formula. So 0.3 times FUK, characteristic tensile strength, times to the diameter to the power of 2.6. So, FUK for our glued-in rod is 500 megapascal. So in the end we get the value of, as you can see here, so kilonewton per meter, in terms of kilonewton per meter would be 1, 2, 3, 4, 5, 6, so 0.3 kilonewton per meter. If you want 275,000 newton per millimeter. And then we need to calculate the bending strength. So for the bending strength, we said we need to start from the bending strength for a bolt. So this formula here. So 0.082 times 1 minus 0.01 d times rho k. So this will be FH, the embedding strength for a bolt. And then for a beam, the CNR regulation said that we can increase this value by 25%. So for our gluing rods, it will be 1.25 times 0 times this relationship here in terms of embedding strength on the beam side. Because on the beam side, you can see here the rod is glued perpendicular to the grain, and so we can expect the embedding strength to be higher because the wood is stressed parallel to the grain. Then, for the column, well, okay, first we use the value in our case, we get 35.7 megapascal, and then for the column, on the column side, the CNR regulation said that we have to take only 10% of the value that we found before. So 10% is 3.57 megapascal. So very big difference between the behavior of the beam and the column, because the wood is very anisotropic, which you know very well. So we can calculate this beta coefficient, FH2 divided by FH1, which is 10. So those are the tables that give us for the rods. For the rods, we said that a threaded rod has the same classification as a bolt. So we need to refer to the Eurocode 3. So this table is taken from Eurocode 3. Instead, for the wood, of course, we refer to the Eurocode, to this regulation, which is a EM regulation for GL28H. We have characteristic density 425. And then we have to calculate the different Johansen contributions, so those 6 different failure modes. So the first one will be basically embedding, pure embedding in the beam. So this one is embedding in the beam. The second one is pure embedding in the column. And then we have pure embedding with in the both beam and column with rotation, global rotation of the fastener. Then we have plasticization. So embedding and plasticization, one plastic hinge formation. The first one is in the column, the second one is in the beam, and then the final one is 2 plastic hinge formation. So embedding plastic hinge formation in both the column and the beam. Now we replace, of course, the value, and we find out. Now we can see, unfortunately, here I don't know why the setting here is quite bad. But anyway, the minimum one, since in our case the rod is very long, quite long, the minimum value is the one associated with the last failure mode. So the failure mode will be characterized by embedding in both timber, so both beam and column, with 2 plastic hinge formation. So this is the summary of the different values of the value characterized with the different value of the strength associated with different failure modes. Then we calculate the rod effect, which is 1/4 of the withdrawal capacity. The withdrawal capacity is calculated using this relationship here. So the withdrawal capacity of the rod, if you remember well, we designed the rod in order to make sure that the rod will yield before then having a failure for bonds or having a failure to move. If you remember, we applied this 1.5 coefficient yesterday. So the withdrawal capacity of the rod will be the area of the rod times the yielding stress of the rod. So 73.5 kilonewton. So the rod effect will be 1/4 of 73.5 kilonewton for not for the first 2 modes, for the other 2 modes. The value of the rod effect we can consider, we say, is up to 100% of the Johansen value. So in this case, we can take all 18 kN, all 18 kN, all 18 kN. Here instead, we cannot take all 18 kN because it's up to 100% of the first step. So here we need to take only the first step, 9,436. We do then the sum, and we find that, as predicted, the last value mode is the one that's going to occur, and the value of the resistance is 18.5 kN. So now we are able to find out the design shear strength per watt by replacing FVRK in this equation with 18,453 newtons. So if we replace all the value, we find out that the design shear strength of the most stressed rod will be, let's say, 9 kN. And now finally we can do this check about combined axial and shear resistance for roding. If you replace, you see the value inside. The last one, you see, the first ratio is a quite high utilization ratio because it's almost the same, so it would say here it's probably more than 90%. Here, it's a utilization ratio between, let's say, 2 and 9, so it's around, let's say, probably 30%, 20 to 30%. So you see 0.96, 96%, 21%. So 96%, 21%, if the interaction would be a linear interaction criterion, of course, it would have been satisfied. We would have to do 0.96 plus 0.21 would be 1.17. Since we are using a quadratic interaction criteria, as you can see, 0.96 squared plus 0.21 squared is 0.96. So it's not a huge difference. Because when you square, of course, this becomes much less. So in the end, the verification is satisfied. So this is the final design of our joint. So we need to do, of course, a drawing where we need to put all the dimensions of our materials, all the properties. So glue laminated timber GL28H, 520 threaded rod class 5.6, glued with epoxy resin in most 525 mm, cross section, indication of the drain, and all the sides. As I said before, this is, you see, it's 1.6 meter. This is 1.71. So the beam will be 1.6 meter high, and the leg of this portal frame will be almost 1.8 meter deep. So in the end, it's a very big joint. Using, you see here, theoretically, here we should use one. So the rod should be 2.6 meter long. So think about how would be possible, how much difficult would be to glue a rod which is 2.6 meter long into a hole which is 5 mm more than the rod. Of course, you can put it inside, but then who can make, how can you make sure that the rod will be exactly in the center of the hole? So you need to, I would say, every some centimeter, you need to put some small spacer. You can't have like the whole round spacer because otherwise the glue wouldn't go through. So you need to have some small space. So what I'm saying is that the process to build this connection here would be extremely expensive. To make sure after that the glue can go through, you can get the actual glue behavior. Okay? So my suggestion for this kind of connection, which are quite used in Italy, is first that you do all this gluing process in a workshop. So never do a joint like this on the building site, because the results will be awful. And the second thing, you should use this kind of connection for smaller joints, not for big joints like this. So smaller joints, let's say beams which are this size, not beams which are that size, because it's very difficult to make it work. So you can do it, but you will never know whether the glue is effective. And so in the future you may possibly suffer from some problems. so this was, as you can see, was a quite long work example. Also because, again, this is not an example of check. It's an example of design. So as you probably realize, also in the previous course about reinforced concrete, it's much easier to do a check, only a check of an existing structure, than to do the actual design of the structure. Because you do the design of the structure, you need to make some assumptions, then to see whether it works, if they don't want to change, and so on. But of course, this is what 90% of the cases, this is what we are called, this is what an engineer has to do. He has to do a design, not a check. Okay? So this is, my opinion, is useful to understand the process. And of course, it's crucial for a course like this that you apply this process here in your design. In fact, now we are going to talk about designing single-story industrial buildings, and we really would like, and also the weight of this, the final score of this course, the weight of your design, of the project that you're going to do will be important, because this is a crucial point for a course like this to do an actual, that you do an actual design, because otherwise if you just study this, of course it's not enough to be able to do your own design. So, now we, as I said, we start with this new presentation about single-story buildings, just to give you some advice on how to organize a single-story building and also how to design it and make it work like it was yesterday evening. I don't know why, what's happening over the night. I have no idea. Anyway, so this presentation is about, as I said before, single-story timber buildings. And we want to provide some concepts for designing a single-story industrial or timber building, which can effectively withstand vertical and horizontal loads. This is also, as I said, the main design project that you are asked to do in this course. So I want also to provide you some advice on load combination and so on. Even though you will see more in detail some presentation of this with Dr. Sementa starting from Monday. So we will start by checking, by listing all the different structural elements, so the main frames, the strengths, girdles, girts, and so on. Oh, some of this work, for example, girts. Girdles in Italian is arcareccio. Girts doesn't have any translation. We haven't found any translation. Girts is a member. It's a manual member that we use on the wall, basically, to connect, like a purlin, like an arcareccio on the wall. We haven't found any translation for girls, so just to advise that not all these words have some translation in Italian. Then, of course, very important, resistant to vertical and horizontal loads. So how to organize the single-story buildings in such a way that they can effectively withstand vertical and horizontal loads. Just one, if you want, introductory thing about this. Some of those concepts will be, that we give for a timber structure, will be exactly the same for a steel structure. So there are not much difference in some respects talking about a single-story buildings made of steel or made of timber. I would say that even a single-story buildings made of precast concrete in some way will be similar to what we are talking about. Of course, now we will talk about timber members and joints, but in terms of organizing the building to make it able to resist horizontal and vertical loads, I would say that this kind of structural system is almost material independent. Of course, if you do it out of cast in situ concrete, it will be completely different. But nobody will do a building like this out of cast in situ concrete. So it's always kind of prefabricated building. So many of those concepts can be easily extended also to other materials. This is the remark. So we will talk about bracing, controventi, basically in Italian, erection, and design procedure, something about load combination, and also the kind of 3D structural model that you will have to implement in a software, for example SAP 2000, in order to study the resistance of the building under the different load conditions, and of course some formula for preliminary design. I would say, first question mark, how are single-story timber buildings constructed? So this is the typical skeleton of a single-story timber building. So as you can see, there are some structures repeated. This main, what we call the main frame, which is repeated more times. The frames are connected on the roof with the pyramids, arcarici, and they are connected, as you can see, on the walls using these horizontal timber members called girts. Then, as you can see here, if the base spacing is quite large, we have to use also some intermediate column. Those intermediate members are not needed for the resistance to the gravity load, are just needed to make sure that the panels, the cladding that we use along the wall will be supported on a span which is not big. So basically, the idea is that we have a structural skeleton and then we put some cladding all around. To close it. This cladding is usually made of lightweight material. So it's a iron, so it's a sandwich panels made of steel. And of course, since they are not very resistant, they need. I'm sorry, I thought that you have something to ask. Yes,
if these girts and columns.
Yes,
columns,
this one.
yes, can be changed with panels with plywood. Or
No, even with plywood, we need those girts because usually the plywood panels they come in a very small size. So we're talking about 1.2 meter by 2.4. So those are needed to support those panels because also if you use sandwich panels made of steel, they are not very big. They are usually quite small. So for this reason, they need to be supported on the four sides.
Have to be
Screwed, yes. So those are, in fact, those members here, they are designed only under horizontal loads. They don't take any guide. I was saying, for example, this intermediate column is not a real column. This one, as you can see, it's only designed to resist. It's designed to bending and shear to resist the action of the wind, or I would say mostly the wind, because the seismic is almost is not a problem. The wind acting on the facade. So the wind that is transmitted by the cladding to directly, so it's directly to this column here. Okay. Of course, the distance between those horizontal members here is really connected to the type of cladding that we are using. In some cases, there are some examples, for example, of very heavy claddings using reinforced concrete panel. In this case, perhaps you don't need it because those reinforced concrete panels are like a cantilever. They are supported by a foundation here. They are very heavy. And they stand alone like almost a cantilever, I would say. However, if you design a lightweight structure, so a lightweight structure made, I would say, a structure like this made of either steel or timber, try to use also lightweight cladding, because otherwise, as you know, when you go to do the seismic verification, doesn't work well a structure which is very lightweight with some very heavy cladding. Because then heavy cladding means that also it transmits quite significant seismic forces on the building itself. Okay, so if you want, the main structural members here are basically the frames and the pyramids. The other members, as we will see, are less important. Of course, they are important because they need to be designed, but the global resistance of the building is taken by the frames and by the pyramids. This frame, we said main frames, they can actually be made by portal frame, trusses, or arches. The different type of system. So here you can see a typical portal frame. In a typical portal frame, of course, you have that the members and the joints, they are mostly subjected to bending. So this is a frame made of blue laminated timber, and this is a frame made of LVL, laminated Indian lumber, with some rigid joints. Usually, we have to the frame is not the frame. In general, the frame doesn't come as an only piece. At least it's made of two pieces, so the two parts, the two halves. Then the two halves have to be connected in the middle on the apex using the joint. In this case, for example, we have one member, one LVL member from the column, one for the beam, another one for the beam, another one for the column, so 4 members. And here we have some rigid joints made using, again, plywood and nails. In terms of restraints, usually these frames are either 2-pin portal frames, as you can see here above, or 3-pin portal frames. Usually we don't have fully fixed frames, which means frames with a fully fixed connection at the base, because they are also more expensive. Of course, the joints need to be rigid to transfer any moment. A 2-pin frame like this, of course, can resist vertical loads. It can also resist to lateral loads. So vertical loads will mostly load in bending the beams and also the columns. Lateral loads will mostly load in bending, as you can see, the joints. Of course, in the reality we will have both vertical and lateral loads. And so we can expect to have the maximum bending moment at the knee. So the knee we have bending moment due to lateral force and bending moment due to vertical forces. So the most stressed part of the structure is actually the knee. In terms of connection of the main frame to the foundation, we have different possibilities. The most common one is a pin connection. Pin connection means that, as you remember, we have to transfer shear and axial force. And so in terms of pin connection, usually we tend to connect only the middle part of our cross-section. So if we want to transfer the shear, we need to connect only the middle part of our cross-section. For example, using these steel angles with some bolts. This is another possibility using glued-in rods. You see, the glued-in rods are closer to the center, they are not very close to the edges of the beam. Because if you put the glued-in rods closer to the edges of the beam, the joint becomes what kind of connection? So a fixed connection. You can see here an example of fixed connection. In this case, we need to connect mostly the lower part of our cross-section using, for example, bolts in order to transfer the bending moment. Then we have to create, as we said before, a rigid connection, rigid joint between the portal leg and the portal rafter. Of course, as we already anticipated by doing the work example, this region here is a bit problematic. Because in this region we have a very significant difference. Of course, since the timber is anisotropic, in this region here we have a very significant difference between the compression strength parallel to the grain, perpendicular to the grain. Think about here, for example. Here we have contact between wood parallel to the grain, so strength 45 megapascal, and wood stress perpendicular to the grain, strength 1/3, actually less than 1/3, 12 megapascal. Now also in terms of stiffness, modular of elasticity in this region here is 10 to 13 gigapascal, and this region here is 1 megapascal even less. That's a huge difference. So when it comes to transfer and bending moment, the bending moment can always be considered as a couple of forces. So this bending moment, it's a couple of tensile force running here and a compression force running here. The same this one, tensile force running here, compression force running there. So the first thing to do is to make sure that the tensile force may be transferred from one member to the other. How can we make sure that the tensile force can be transferred for the two members? If here we have a discontinuity, we need to add one element, for example, rods that we done before, or a plate, something continuous that makes continuous and that may allow this axial force to be transferred through this continuity. The first thing to do is to make the tensile force to be able to be transferred, so to make some continuity on this discontinuity here. Then, of course, this member here may be glued, like we said before. If this member here is glued in this member, in the other one, then it's good because we don't have a stress concentration in compression perpendicular to the grain. However, gluing this member on the beam is problematic because we said before we have to avoid gluing on the beam inside. It means that in a joint like this, you would have to do the whole joint on the workshop. This you can do it, but then you need to transport this member to the beam inside. And so you are limited, of course. You can do a transportation of half frame only if the sides are not too big, because otherwise you cannot fit on the loading. After it becomes an exceptional transportation, it's very hard and very expensive to do. So for this reason, a solution, practical solution to solve this issue, consists in gluing the member only on one side, for example, only on the column, and then just to insert this member into a hole prefabricated on the beam. But then, of course, if you cannot glue it, you need to put at the end a big steel plate in order to make sure that there will be a contact between the steel plate and the beam itself. So we can do it this way. However, if we do it this way, you see, when we apply this bending moment, we have this region in yellow where there is an exchange of compression forces between the steel plates, which is welded to the rods, and the timber of the beam. And in this region here, as you can see, we have compression perpendicular to the grain. Compression perpendicular to the grain means that we have a lower strength, the beam, so we may have failure, but we may also have material which is much softer, so we may also have significant deformation. So very important deformation due to the low modular of elasticity. Meaning that when we apply the bending moment, we may have a rotation of the joint. So the joint, we design the joint as a rigid, but in reality it becomes semi-rigid. Because due to this deformation, the joint is going to, the beam is going to rotate in the air. So we are going to have a relative rotation of the beam with respect to the column. And this rotation can be quite significant due to the flexibility of the wood perpendicular to the ground. Okay? In addition, we have also, you see, compression perpendicular to the grain on the other side. So here we have a transfer of this compression force due to contact between the timber of the column and the timber of the beam. So for contact, for simply contact, without gluing anything, we can transfer the compression from the column to the beam. But again, here on the beam side, we have a problem of compression perpendicular to the grain, so smaller strength, but also higher flexibility because the R modulus is very low. So again, here we may have an indentation of the beam, meaning that, again, another contribution to a relative rotation. So we can have a relative rotation of the beam with respect to the column due to the compression of the beam timber here under the steel plates and the compression of the timber of the beam above the column. So both these contributions are going to make this joint not rigid but semi-rigid. So the joint is going to open. So, in order to prevent crushing perpendicular to the bed this flexibility, one possible remedy is to distribute load over the faces of the members. Which means, rather than having only one bar here, only this region here, it's better from the structural point of view, for sure not from the aesthetic point of view, it's better, you see, to have a big steel plate extending from the column to the beam in order to distribute all those stresses not only one small region, but over a large region of the beam. So this, for example, is an example of nailed steel gusset plates. So big steel plates with several lines of nails that transfer the bending moment from one side of the beam to the plate itself, and then from the plate to the other side of the beam. For sure, here we don't have concentration of stresses, the formation diagram in the case that we saw before. Of course, these steel plates may be replaced by plywood gussets. So again, plates made of plywood rather than steel, with more lines again of nails. In this case, as you can see here, we can have nails that are bent to the timber using this kind of guns here. We can also use plates made of LVL to have this connection here, this rigid connection between the rafter and the column. Or we can have what we call cross-lap glue joints. So a joint between, you see here, it's like having kind of finger joint if you want, where this surface between the column and the rafter are glued together. But again, here there is a problem if we have to do this gluing on site. So this kind of joint should be done in a workshop, but this is going to limit the size of half portal frame that you can do, which of course after you transform the big inside. This is another possibility. In this case, as you can see here, the cross-section of the rafter and the cross-section of the column, it's a kind of box section. So we have, for the column, we have a section like this. So this is plywood, this is glue lamp, and here we have some nail connection. So this is a cross section of the column. Then the beam is more or less the same. Of course, here you insist that these plywood panels, as we said before, they are 1.2 meters by 2.4. We need to have some joints. You can see here a vertical joint, for example, here, meaning that elevation, the beam will be diminished. this would be the plywood pattern. Okay. So it's clear what they sketched on the blackboard. It's basically a box beam, which is prefabricated using glue solid members and plywood panels on both sides, which are nailed on the beam itself. In this case, you can see that this beam here has an inclined end, so here in the end, do something like this. And this piece here is connected to the other piece of the column using here a steel profile. This is again to get rid of this problem with the anisotropy of wood on the cover, basically. On the right, you see another very common solution for moment transmitting joints, which is this double cross-slab joint. So here we have a solution like this. So we have a column made of glue of LBL, and then we have the rafter, which can be made of two halves, like this. And the connection is between these doubles going both members. So this is basically looking down situation like this. This is actually made of NBL and NBL, but made by glue laminate. In this case, we have, as you can see, two lines, two circles of doubles. Note that at least 4 doubles, so 1, 2, 3, and 4, are characterized by, they have at the two sides some washers in order to ensure that these two parts will not fall apart. If you remember, one problem of the double connection is the double is just a cylinder of steel. It is tight fitted into the wood, but it doesn't have a withdrawal resistance. So it means that if you only use double, suppose that you have some problem. So for example, someone is pulling down, is pulling this side here, so this one could come outside with very little horizontal forces. In order to prevent this, take into position, at least we need to put some of them, at least 4, must have these plates and to act as a bolt in order to ensure that they cannot, they have some withdrawal resistance. This is the solution that we already saw before. If you want to use glue connection, the best way is to get rid, as you can see, of this part here. So this part, you can just use steel. And this steel hub here is then connected to the portal, so it's connected to the rafter and to the leg of the portal using epoxy glue rods. In this case, the beauty of this solution, if you want, is that you can prefabricate, you can do all the gluing on the fabrication line. So you arrive on the building site with the leg with already glued in the epoxy rods, with the rafter with the already glued in epoxy rods, and just then connect on the building site these rods with the steel plate. Then, of course, you can cover those steel plates with some small panels of timber in order to make sure that you have a better appearance of the structure. Those levels of steel. This is another solution for rigid joints. In this case, you see there is a big steel plate with some holes that has been slotted inside the two members, inside the leg of the portal frame and the ring. Of course, in this case you have some advantages because the steel plate being inside the wood. First, it's a better aesthetic appearance, so you don't see outside the steel. And secondly, you have also a larger fire resistance. When we are talking about fire resistance, you will see that contrary to what one may think, it's better to have outside wood rather than steel. Wood is combustible, steel is not, but wood is also a good insulator, while steel is a good conductor. So if you expose outside a timber structure steel plate, in the case of fire, the steel won't burn, but it will conduct very quickly the heat inside the wood. And then you will have lots of problems inside. But instead, if the steel is inside the wood, in some way the steel is protected by the wood. So the wood will burn outside, but then, since it's a good insulator, the steel will still be at a lower temperature because the wood is going to actually insulate the steel itself. So in terms of main frame, we said one possibility to have this 2 or 3 pin portal frame. The other possibility is to use truss systems. You can see different possibility here. For example, those are truss systems made of glulam members and steel plates. So the connection is achieved using steel plates, nailed steel plates, for example. Or in this case, we have the vertical members is made of round wood, and then we have this big truss made of timber. Unlike portal frames, in truss systems, the resistance to the global bending moment is achieved through axial resistance of the members. So in this case, we have a global bending moment resistance, but the single members are loaded in axial force, not in bending. So you will have, for example, here tension in the lower member and compression in the higher member. So we designed those members for axial force, not for bending. This kind of connection is very much used in the Anglo-Saxon countries. Those are called punched metal plate fasteners. Those are plates made of steel, which are punched in order to get some tooth out of them. And then those tooths are basically pressed inside the timber using some presses. You can see here, this is what we are talking about. So this is the punched metal plate. Why punched? Because in the fabrication process, initially you have a steel plate with a very small thickness, and then it is punched in order, you see, to bend this kind of teeth here. Those teeth are then used to connect, those teeth of course will penetrate within the timber using this press. So you see here the manufacturing process. We have different small timber members kept together perhaps using a single nail. Then some of those plates are positioned above the joints, and then with this press they are pressed inside. So in the end, this metal plate with those teeth is going to connect the different timber members. So it's the single tooth which makes the connection between the timber and the steel plate itself. arches. So the arch is a great structural form to resist vertical loads, because in an arch the main force due to vertical loads is compression. So you can say that an arch resists the global bending due to the horizontal force through compression due to this shape. Okay? However, we need to remember that an arch, in order to work as an arch, not as a beam, what kind of restraints should have at the end of the arch itself? So if you want an arch, from this arch, to be mostly subjected to compression rather than bending, what kind of restraint do we need to put here and here? No, usually we don't use a casting because it's too expensive to do the casting. This way. Are you sure about this? Because if we do it this way, what's happened? What would be the most important? Yes, so if we do it this way, once we apply the load, this one is going to deflect to the form in this way. And the main force, internal force, will be what? No. No. Two more possibilities. Tension and bending. Okay, tension, last one. Last one is bending. So if we don't prevent, let's say, this possibility of the arch to enlarge, the main the main internal force you will find is bending moment. So this arch will behave exactly like a beam. The only difference being that it's curved. So this would be what we call a curved beam. Okay? Instead, if we prevent this displacement, so if we consider 2 inches, then you will find that this is a real arch. So then you will find that in this case, since we have a restraint reaction, in this case, the most important internal force would be compression. So remember that in an arch, it's very important that you prevent the displacement at the restraint of the arch itself. This is why you can see here in this arch, this is a very big arch, it's a 3-beam arch, you may see there is also a beam in the middle. This one, which is a very big arch, you can see that at the end here there is a pin. This one is a real pin made of steel. And here you can see that there is quite a squat reinforced concrete cantilever. So this is a reinforced concrete cantilever, exactly a structure made in this way, by reinforced concrete. So, why, for example, here they use reinforced concrete on timber? Because if they had used timber here, the deflection would have been much higher. Because I just remind you that timber and reinforced concrete have more or less the same cross section. So here a structure made of timber would have had more or less the same size. However, the horizontal deflection would be, in case of timber, how many times the one of concrete? Remember, more or less? Not 30%, much more. And yes, if we were to, let's suppose that we have done the same structure here made of timber. So, a structure like this made of timber, first of all, which size would it be? If I'm going to do the same structure here made of timber, in terms of strength, how would be the cross section? Larger, smaller, or the same? More or less the same. Because if you remember, the strength is more or less the same. Okay, now in terms of deflection, we said before that to ensure that this arch will be had as an arch, not as a curved beam, we need to make sure that the deflection here, the horizontal deflection, is quite small. Okay? So we need to have a fixed, well, no, sorry, not fixed, a fixed deflection. So meaning that here the deflection must be quite small. Now, the question is, if I'm going to build the same structure made of timber, which will have the same cross section, what kind of deflection will I have here because of the arch? So this arch is basically pushing here, so I'm expecting to have a deflection. So this is like a cantilever subject to a horizontal force. If I do this structure here out of timber, I will have the same cross section. So, what kind of deflection can I expect as relative to the structure made of reinforced concrete? Smaller, the same, greater, and how many times difference? Greater, how many times greater?
It depends on the elastic modulus.
It depends on the elastic modulus, so we need to make a comparison between the elastic modulus of timber and the elastic modulus of concrete. What is the difference between the two? More or less, the elastic modulus of concrete is how big? The typical elastic, if I have to ask you, yes, but that's correct, but let's just do the reason from the thinking from the very beginning. What is the elastic modulus of reinforced concrete? More or less. 30 gigapascal. It's 30? Yeah. No, I think it's 3 gigapascal. Because it's in terms of megapascal, would be 300. I mean, I still remember the value in kilogram per square centimeter. 300,000 kilogram per square centimeter should be. So in terms of megapascal, so 1 kilogram per square centimeter is it's 10 newton per square centimeter. So I will do a transformation now. That's it. Anyway, it should be 3 because 300,000 kilogram per square centimeter. This will be 3 million newton per square centimeter. And then newton per square millimeter, 3, so we need to take away 2 zeros, so it will be 30,000. So let's see. No, I think it's right. So you said, what you said?
30 gigapascal.
30, I think it's right, because 300,000 kilogram per square centimeter would be 3 million newton per square centimeter. And then to get newton per square millimeter, we need to divide by 100. So this would be 30,000 newton per square millimeter, which is megapascal. So gigapascal, we need to divide by 100, so it was right. So 30 gigapascal. One is that timber, for timber, is basically 1/3, as some of you were saying. So it's basically 10 gigapascal. So since the cross section is the same, basically if the young modulus is 1/3, the deflection will be 3 times. Okay? So for this reason, also for this reason, you can see here, this squat cantilever was made of reinforced concrete to make sure that this deflection here is very small. Because if they had done this out of timber, the horizontal deflection would have been 3 times. And then we would have a behavior not very good as an arch, more as a curve. Okay? Okay, we said that then we have another important structural member which is called purlins or arcarecci in Italian. So those members connect the top of our portal frames. The purlins can be done in a different way. They can be made of lula meaning timber, like here. They can also be made of truss systems, like here. They have two very important, or actually I would say three important functions. First of all, the purlin is there to resist what kind of load, in your opinion. So when I put a horizontal purlin on the roof, what do I need this member? To resist what? First of all. Vertical gravity load, snow, wind, whatever it is. This is the main reason. But this is not the only one. There are also other two important functions. The other two important functions are provide lateral torsional restraint to the main frames. Remember when we did a verification for lateral torsional battery of this 22-meter beam? At the beginning we said, okay, let's consider no restraints. 22 meters, we had a reduction in strength by, I think, 90%. So the strength of the beam was only 10% or maybe 15% of the actual flexural strength. Too low. So we need to provide some restraints. And those restraints are provided by the purlin. First important function. Second important function, the purlin, as we will see shortly, also are needed to transfer the loads, the longitudinal loads, due to seismic, so the horizontal load, the seismic or wind, to transfer those loads down, if you want, to the bracing system. So we will have to design the purlins in order to take into account all these functions. This is a special kind of purlins, it's not much used in our country. It's a high purlins where we have LBL flanges and glide webs. Girds, we said, are those horizontal members running along the walls. Here you can see the girds. You can see here the cladding is made of steel, so metal plates here, or sandwich panels, and they are supported by horizontal girds and vertical elements, because they need to be supported to reduce basically the span, because otherwise they would reflect too much, because those members are made of a very thin corrugated iron, which needs some support, because otherwise it will deflect too much. So these girds support both cladding, resist wind load, and provide some restraints against lateral buckling together with wall cladding for the main frames. Purlin and girds are typically connected to the main frame using pin connection. You see here different possibilities for the pin connection. So never with joints, because they would be too expensive. So the connections are pin connections. Typical connection between Lula, Burley and main frame, which is angle brackets. So the Lula Burley is supported by the angle brackets. Compression perpendicular to the blade, the angle brackets is connected to the main frame using some screws. Now, in terms of stability of the whole structure, in respect of three-dimensional stability of this structural skeleton. So if we have, for example, these two-pin portal frames connected longitudinally using purlins, pins connected to the frame themselves. The first question that we can ask to ourselves, is this building system stable under vertical loads? So is the system well designed under vertical loads? Do we have problems for resistance under vertical loads? What is your answer? Yes or no? So if I apply vertical load anywhere here at any point, can I transfer this vertical load to the foundation without having any trouble?
Yes, yeah.
Yes. the system is definitely stable. So for example, if I put a polygon here, this will go probably 1/3 on one side, 2/3 on the other, on the frame, and then from the frame down to the foundation without any problem. Okay? So for vertical loads, no problem. Now for horizontal forces, horizontal loads, wind for example. So if I have a wind blowing this direction, if I apply, if you want, if I apply horizontal point load on the facade, the lateral facade, can this load get its way down to the foundation?
Yes.
Or not?
Yes, because it is in the direction of the...
Yes, correct, because it is in the plane, parallel on the plane of the frame. So this one again will go probably 1/3 here, 2/3 on the other side, in some way. And then, of course, from the frame we said before, the frame is either 2 pin or 3 pin. Anyway, it's there. Can resist any lateral load. So this is okay. So, some example of in-plane stable systems. You can see here different examples. What we considered before as a typical one is the solution number B. Okay, this would be a total frame pin on the base, which could be a notch, could be a truss, and so on. Another possibility, which is less used, I would say, for pin, but perhaps this one is more used for precast reinforced concrete. You can have some columns, which are prefabricated columns, which are fixed on the foundation, and then we have some prefabricated beams, which are being connected to the top of the column. For example, this kind of precast buildings that we had in the Laurea Padana, now when there was the earthquake, there were a system like this, more or less, and which was stable. The only problem was that the pin was actually not a real pin because they were, or at least on one side, they were in some way the resistance to shear was simply due to friction because they were simply supported. So this was not a real pin on one side, but was a pin with a rotor because they were basically just simply supported and they were relying on the friction. So when the earthquake struck after l'Aquila in Laurea Padana, the problem was that this one started moving on the opposite side, and the friction was warm in some way, so it was lost, and then simply this beam fell down. Okay? Anyway, but this is another system that we don't use for timber, this kind of system, also because it's very difficult to realize an actual fixed connection, or we can have this kind of system here, typical cross-pressing system. So here we have pin connection, pin, but we have the two diagonals, for example, using rods. Why is this system not much used? Because, of course, if you need to work inside the workshop, this is going to limit a lot the space available. So this system here can be used at the cables, so at the end of the workshop. But also there sometimes you need to have a door to enter to allow, for example, the truck to enter inside, and of course this diagonal may have an limitation, may limit the space. In this case, if we use system C, meaning that, for example, we use one system here, and one system there at the cable, we need, in order to make the system stable, in order to make sure that general lateral force may be transferred to the bracing. So in other words, what we are saying now, if this is our building, so this is, only at the end, we have a system like this. Okay, so here and here we have a system like this, which is stable. And in between, we have instead a system, a series of systems like this, which is unstable in plane. So here we have a system done in this way. So this will be this system. While here we have a system done this way, which is unstable, okay? Because these crosses cannot stay inside, because otherwise you don't have room enough. So here we have a stable frame, unstable, 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 unstable. Okay? So is the global system stable if you done it this way? By, of course, those members here are connected on the top with the pyramids. Okay? Now my question is, this system done in this way, is it stable? So can we transfer a generic, for example, horizontal load applied here on a system like this, where we have only two frames, only the two end frames are stable and the other one they are unstable? Yes or no? Yes? Are we all sure about this? So how can I transfer this horizontal force here to this? Eh?
You don't have basic systems.
For the time being, the only basic system is here and here. Only here and here. The one in between, they are done in this way. So if I push here, how can I make sure that this force will be transferred here and here?
With burdens.
Eh?
With burdens. With a garage.
Yes, but are we able to do so? If the burdens are ill-connected with the frame? Do you remember, we said a few words 2 years ago, 1 year ago about this, but now we need to. Because after we work with the casting situ reinforced concrete, we don't have any problem, because we have a monolithic floor, but here we don't have a monolithic floor. Because here we have the panels, like cladding panels, which are connected with the purlins. So for sure here, the floor is not monolithic. So who is going to transfer this horizontal force applied here? So this one is, for example, this frame. I'm pushing here. Who is going to transfer this force to the two frames, two places? I don't have a casting situ floor, roof. So some of you said the pyramids, but the pyramids, they are ill-connected. So on a system like this, if I push here, what's happened? How is going to deform the system? Assume that your pyramids are infinitely rigid.
You can translate on the bin connection can translate.
Yeah. So this one, okay, now I look for the sake of simplicity a simpler system like this. Okay? So this is braced, this is braced, this is unbraced. Just for the sake of simplicity. If I push here, what's going to happen? Sorry, I just missed one purlin here and one purlin here. If I push here, so how is going to deform this? Is it able to transfer this force here or here? This purlin is infinitely rigid purlin. So? I would have something like this. So the system will be clearly unstable. Okay? Even if the purlins are very rigid. Why it will be unstable? Because the purlin is very rigid, but the connection between the purlin and the frame is weak. So the system is unstable. How can I make this system stable? Well, the criterion is what we already learned, what we already discussed in the reinforced concrete. We need to make the floor must be in plane rigid. problem here is that the floor is not in plane rigid, it's not rigid. So what I need to do, I need to make the floor in plane rigid. How can I make this floor in plane rigid? Yes. Either I need to use very stiff panels, in plane stiff, could be the plywood, but not sure if I use these sandwich panels, unless I don't nail it all along the whole perimeter, this is not enough. So I need to add some bracing, in-plane bracing. The in-plane bracing, for example, is something like this. If I put some diagonals, then actually this diagonal only on one plane. I don't need to put three diagonals, only just one plane here. If I put the diagonal between, these diagonals, they are going to make the plane, the roof in plane rigid. Okay? Because then now, suppose, for example, here I apply the force system like this. I apply force here, I put the diagonal. This diagonal is going to, this one is going to react in tension, this is in tension. So this force will be transferred here on the bracing through these two diagonals in tension. Okay? So what we learn, this is very important actually, because this is criteria must be always satisfied also for steel warehouses, for single-story industrial steel buildings. If we have only a stable system only at the edge of the buildings, in between I need to put some bracing, floor bracing like this, as you can see here, to transfer the horizontal forces from the inner point of the structure in the end. Conversely, if I use, like before, a frame which is 2 or 3 mm frame which is stable, so all of those frames, if all of those frames are stable, then I don't need to use this in-plane bracing system, okay? Because they are all stable, so the force will be transferred directly. But instead, if only the frames at the two ends are the only stable one, I need to push this in-plane bracing. Is that clear? This is a very important concept, so I'm glad that it's not like the reinforced concrete, we just give, small information that then we didn't use anymore. In this course, this information is very important, so you need to understand very well. Now, resistance to lateral load. What about the resistance of this building, which is made of in-plane stable frame, to a load applied out of plane? Is that stable? Can I transfer this load down to the foundation? And how can I transfer this load down to the foundation? Is it unstable? Are you sure it's unstable? Yes, because you see here there is a pin connection. I could make this system here stable only if I was using here a fixed connection. So if I'm going to connect those frames with a fixed connection out of plane. So now we're talking about a frame which is a plane structure. The frame may have a pin connection in the plane and may have a different connection, for example, a fixed connection out of plane. So this could be a pin in plane, but in order to make it stable in the longitudinal direction, it should be fixed out of plane. It's clear what I'm talking about now. So looking in this direction, this is pin, and looking the other direction, I would need to have a restraint like this. So if all these connections here are fixed, then since I have a connection here with the purlin, this force will be transferred and resisted by the different cantilevers. Okay? this is a pin connection in plane and out of plane, I would have a system like this, which is clearly unstable. Okay? In general, we design a structure like this with pin connection in plane and out of plane. So we never design like this. So we are in this case here. So meaning that the system is unstable. So how can we solve the problem? How can we make this system here stable? Using a bracing system. What would be the simplest way of using a bracing system? But system, what we said before, the simplest way is to make at least one base stable. So I don't need here to put two bases, I just need to put one cross here. Then I can connect also here hundreds of other frames, providing that this one is stable. So if one is stable, all the other hundreds frames will be stable, because they are connected with the permits. Of course, if I have to stabilize 100 frames, this bracing will need to be quite significant. So for this reason, if I have a warehouse which is longer than 100 meters, probably it's a good idea to have at least 2 or 3 or 4 of those bracing. Otherwise, I get two big bracing sections. Okay? Okay, is it enough to put a vertical frame to make the system stable? So now we go back to what we were discussing before. This is our case. Permit. And for example, we decide to make here a cross, a vertical cross. So we have a vertical cross like this, a bracing system here and here. Okay? Is now the system stable?
The roof.
What's the problem with the roof?
The roof is not stable. We have to put some bracing also in the roof.
Which bracing should I put on the roof? Like before? Do I need to put bracing like this? No, in the other direction, exactly. This, I don't need this one, because if I apply a force here, I'm okay. Even if I apply a force here, I'm okay. The problem is if I apply a force here, this one will make won't be able to be transferred unless we do a bracing like this. Okay? So in our system, if we use bracing, if we use frames which are stable in plane, to make the whole system stable, we need to put one bracing also in the roof in the direction of the frame. Okay? So I need basically to have at least two vertical bracing and at least one horizontal bracing in the roof to make the whole system stable. Of course, in the case that we saw before, also in that case we will have to put this. So before we said that we have to have a horizontal in the case with frame non-stable in their plane. In that case we say we have to have a horizontal, and in that case, also in that case we have to have this one. So this is for our case, also for the previous case. But for the previous case, in addition, we had to have also this in the previous case, okay? So basically, this is what we have to do. In this case, as you can see, the force can be transferred. Note that in order to transfer the force, you see that we need the purlins. I said before that the purlins are needed to resist the vertical loads, are needed to resist also the horizontal loads. Because this horizontal load for all the wind acting on this frame, on this facade here, will be transferred to the bracing system through the permits themselves. Okay? And then, of course, from the bracing system, note also this is very important. So, the permits will be subjected to axial force because of the wind, longitudinal wind. And as you can see here, then here we have a bracing system. Just what you are now, then I think we have to stop shortly. Just note that in this bracing system, it's not only the diagonal that works. So the diagonal will work in tension. If we use, for example, epoxy, if we use rods, the rod will only resist tensile forces, not compression. So some of the diagonal will be expressed in tension. And those diagonal will contribute to bring this horizontal force down to the foundation. But note that also there are some forces going down through the frame, compression, and to the other frame, tension. So in the end, there is the bracing system of the building that transfer the horizontal forces due to the longitudinal wind to the foundation. It's not only the diagonal, so the diagonal in the roof and the diagonal on the facade. It's also made from the frame itself. So those frames are needed to resist the vertical load, the lateral load, but also the longitudinal load. Because the longitudinal load will basically produce some compression in one frame and some tension in the other frame. Okay? So when we talk about bracing system, it's not only the diagonal of the bracing system, it's also the frame where those diagonals are connected. Okay? This will be important because now, later on, when it comes to design the members, we have to remember that when we are going to design those frames which are part of the bracing system, they will be stressed also by not only by the in-plane load, but also by the out-of-plane load, because they are part of the bracing system. Okay? While instead, in silent frames, for example, this frame here, this one will be designed only under the in-plane loads, not only the out-of-plane loads. Okay? Any question on what we saw today? Today we go a little bit slower on this part, but I think this part of the behavior of the structure in the space is very important. You need to be very clear, to be very clear about the behavior, the three-dimensional behavior of this building, because otherwise you risk to not be able to design the building in the right way, to take into account all the loads that we are going to stress the building themselves. Okay? Okay, so if there are no other questions, we stop here. On Monday, you will do, I'm not sure if you are going to have 3 hours with Dr. Schmidt or 2 hours. So, because on Monday, you will have 2 hours with me when we are going to continue this topic here from 5 to 7. So, only the last 2 hours. Then before you are free, I think also from 2 o'clock, either you do 3 hours with Dr. Shomenta, so from 2 to 5, or 2 hours from 3 to 5. I need to ask her. Anyway, I will ask her to send a piece of information in e-learning, okay? So, I know 5 hours is quite a lot, but split in 2 is much better than with the same speaker. The speaker will be 5 hours to make, but perhaps since we are 2, I think we can make it. Because you are free, right? Between 2 and 3. Okay. So I will ask Dr. Shometa to send you an advice on e-learning. Are you all on e-learning, I suppose, now? So if you get an advice on e-learning, the content you will get it. Okay. So we get this advice to understand whether you should come here at 2 or at 3. Okay, thank you and see you on Monday.